Please do confirm when you start the recording.
Yes,
All
we
right.
already started the recording, and here we
All right.
are all to the training session.
All right. So thank you so much, and good afternoon, colleagues. And thank you for participating on this probabilistic record linkage training that is being conducted under Data for Now initiative in Colombia. Talking about Data for Now initiative, it focuses on developing countries' capacity to deliver information needed by policy and decision makers to achieve the 2030 agenda. So in this context, we have worked closely with DANE in various other activities under priorities identified by DANE, like under SDG 1, SDG 4, and SDG 16, like small area estimation, natural language processing, and establishing IT architecture under accelerating implementation for Data for Now project in Senegal and Colombia. Before starting the training, let me briefly introduce you Brian, who would be conducting our training today. Brian is a fourth-year PhD student in statistical science at Duke University. He is advised by Dr. Rebecca Stork, and his research focuses on efficient and scalable Bayesian record linkage. His work is supported by the Alfred P. Sloan Foundation and Google PhD Fellowship. Before handing the training session to Brian, let me briefly highlight few housekeeping rules like please keep your mics off unless you are speaking. And then if you have any questions or so forth, you could just raise your hand or put it in the message. And I would believe Brian would be also stopping by while he's doing his presentations to ask for any questions. And then this training is recorded. So I will just hand over to Brian to maybe start the training.
Great. Hi, everybody. Like Samrat said, my name is Brian Kundinger. I'm excited to be sharing with you what I know about probabilistic record linkage. The presentation today will consist of a set of slides that I've developed, then where I'll talk about some general overview of probabilistic record linkage, and also highlight two pieces of software that of R packages that are used to do this. Then I have one R tutorial that is produced along with one of the packages. It's called FastLink. So I have the official R tutorial that goes along with it, and I'll just skim that and show you some things to look out for. And then I have one second little R tutorial that I wrote, highlighting some additional extra things that I like to look at when I'm doing record linkage. So without further ado, I will start. And go. Okay. Great. So this is Introduction to Probabilistic Record Linkage. And as I said, there's going to be an overall overview, then some practical considerations that you should keep in mind as you're doing this and as you're using these pieces of software, some evaluation metrics and things to look out for, then like the pieces of software themselves. At each of these bullet points, I'll stop and ask for questions, and feel free during to either raise your hand, interrupt me, or type them in the chat. So what is record linkage? Record linkage is the task of identifying duplicate records over noisy data sets. This is easy when we have unique identifiers, like in the United States, social security number, or many other countries have some other type of identifier. And it's difficult when we don't have that identifier or when there's errors in the data. When I'm Brian, B-R-I-A-N in one data set and Brian, B-R-Y-A-N in another data set. Bipartite matching is a specific goal of matching one record in one data set to at most one match in another data set. that is just kind of the most intuitive way we think of record linkage, that each individual list has already been deduplicated. So we're just looking for one best match in the other data set. And the reason why I highlight that is gonna come up later. So I like to start these with kind of explaining just a little bit about also my introduction to record linkage. So I got interested in record linkage because I saw it used in the study of human rights abuses. So this is a snapshot of an article about my advisor, Becca Stortz, who used record linkage techniques to more accurately estimate the casualty count in the Syrian conflict. That was a very, very difficult record linkage problem because we did not have any unique identifiers. People's names were just, you had someone's friend or family telling you afterwards this person's name and birthday and all sorts of stuff. So information is very inconsistent across data sets, and it turned out to be something that probabilistic record linkage helped a lot with. The other kind of broader thing, because I'm talking to some amount of statisticians, is I want to talk about one of the advantages of this probabilistic approach. So imagine we have two data sets, and one of them has, the one on the left, has a response variable and some personal identification information. And another one has that information and then a set of covariates. So you could imagine on the left is some type of whether somebody voted or not, and then I have my name, Brian Kuninger, and address. And then another data set, it has my name, and there it has my age and my income and my race or something like that. And you want to be able to link these data sets, and you want to be able to account for the fact when you do your regression analysis afterwards that you're actually not entirely sure whether one Brian Kuninger is another Brian Kuninger, and you want to account for that uncertainty in the matches in a later analysis. So I can imagine in many purposes, all you're trying to do is link records to have more updated, a more updated record, right? But sometimes if you're doing the downstream analysis task, it can be useful to maintain that probability of being a match for your later analysis. So now I'm going to explain the basic framework that I'm going to be talking about today. It's linkage through the comparison vector approach, which is popularized by Falegi and Center, which I'll talk about in a second. So imagine we have two data sets, A and B, and in A, we have a bunch of these Taylor-Smiths. We have a subset of record of database A and a subset of database B. And we have NA records in A and B records in B. We have capital F 4 features for comparison. We have their first name, last name, their city, and their gender. And we're going to say we're going to characterize the level of agreement on each of these features with this vector L. We have 3 levels of comparison for the first name, 3 levels of comparison for the last name, 2 levels for city and gender. So what that's going to look like, it's a little abstract, is our first one, this gamma 11, is comparing the first record on the left to the first record on the right. And we're going to say that Terry and Taylor are non-match, are in complete disagreement. They are not reasonably close matches. And we're going to give that a full disagreement level of 3. Smith and Smith are exact matching. So we're going to say that has a 1. Durham matches with Durham. And female does not match with male. That's a 2. This is a somewhat arbitrary, not arbitrary, though the modeler has chosen how to designate these discrete values for the comparison. And there's some literature on the best way to do it, and the packages have default settings, and I have some words of wisdom about how to do it as well. But the goal is to take all these records we have and kind of simplify this data down to this down to these comparison vectors. So continuing, second record gamma 2.1 compares the second record to the first record on the right, and that's Taylor, exact matches with Taylor, Smith with Smith, Durham, male. So we're going to get 1, 1, 1, 1 across the board. This last one, we are using 3 levels of agreement to be able to capture partial agreement. So Taylor, Tayler is one spelling of this name, and Taylor is another spelling. And we are going to use a string comparison function that is going to identify this as a near match. So that's going to get this agreement level of a 2. Then again, Smith with Smith, Raleigh and Durham are different, and female and male are different. So again, we're using these comparison vectors to kind of quantify the amount of similarity between the different records in the data. This is what we're going to talk about in a little bit, and you can maybe start highlighting questions. There's a lot of different ways that you can create these comparison vectors and a lot of different functions you could use. So most of the packages that exist just use it's called normalized Levenshtein distance. It's basically an edit distance. You have 2 strings, and how many characters do you have to change to move from one string to the other? That works for a lot of contexts. The team in Dane has already explained that there's something more specific to the Spanish language, right? That maybe you want to, the similarity between a Y and a double L, that's different than the similarity between a C and a P, right? For example. So there's different functions that one could use to construct these comparison vectors. But yeah, this is the basic approach. One set of notation that just comes up in a little bit is this linkage. You don't need to worry that much about this, but we're going to describe the linkage structure through this vector Z, and we're going to say that Zj equals I if record I and A and J and B are a match, and NA plus 1 if record J and B has no match in A. That doesn't matter too much. It'll just comes up on one later slide, so don't worry about that level of math. But basically, it means that we go back to this first example, and if our record linkage model works correctly, we're going to end up saying that Z1 equals 2 because the first record in B matches with the second record in A. And we're going to say that Z2 is equal to NA plus 1. I could have called it and Z2 equals 0 or some other placeholder value just to indicate that Brandon Green does not have a match in A. Again, that's just notation. It's not real math, so don't worry about that. Actually, at this moment, I was going to wait to ask for questions, but this might be a good place to pause for questions if anybody has any. Let's wait like 30 seconds. Okay, I'll continue. So there are multiple different statistical models to handle record linkage, and the canonical one is Feleghi and Center from 1969, very old model that basically most modern approaches to record linkage all benchmark against this method. So it begins by making pairwise comparisons for each pair of records in the data set, in the 2 data sets. So that is NA times NB many independent classifications. You have NA times NB many record pairs, and we're going to independently classify them as a match or non-match. Something that should be going off in your head is NA times NB is extremely large, absurdly large, prohibitively large, and that is going to be a problem in almost all practical applications. I'll talk about later ways that you can get around that, and the fact that other methods are being developed to account for this as well. So you have these NA times NB many independent decisions. This approach with this independent classifications has been shown to be scalable to large data sets. So that is through this one package called FastLink by Ted Inamorato, who I just had dinner with on Friday. And this is the package that I'm going to end up showing to you guys today. Because these are independent classifications, you might not get a bipartite matching. You might have two records in one data set that match to one record in the other. And by your assumption, you kind of know that one of those matchings must be false. This gets cleaned up in this post-processing step, and that it's taken care of in the package. But because of allowing those multiple matches, overall this method tends to overmatch somewhat and leads to somewhat inadequate parameter estimation. In the case of Danny, it seems like this is going to work really well because you, despite these shortcomings, because you have a nearly unique identifier from what I understand. So this is a shortcoming that just to be aware of, but I'm still going to end up recommending FastLink to you all. Just to give you all, a little bit of additional rigor on what this model is. It's essentially a mixture model. So we're going to posit that these comparison vectors come from two different distributions, one for matching record pairs and another for non-matching record pairs. And so this model is going to learn the parameters for each of those distributions and independently classify records as matching or non-matching. Just to give you guys a sense of other approaches, and to give you a sense of what I research and what I'm developing, there's another method called beta record linkage by Mauricio Cedinle, who is Colombian, and was a professor for a long time at University of Washington. And this inherently produces a bipartite matching without the need for this post-processing. So the way it works is we have NB, many dependent decisions. That's a decision for each record in the smaller data set. And when I'm going to match this first record, I'm kind of going to ask, okay, what's the best one that I can match to? And let's say, for example, I match it to the first one on the left. Now what happens is that when I look at this second record, that first previously matched record is no longer a candidate record for the matching. And so this approach, it strictly enforces one-to-one matching with no need for this post-processing. This makes this record linkage technique more accurate for the linkage itself and for these model parameters that matter to statisticians, probably don't matter as much in many practical applications. But this method of maintaining the amount of work it requires to maintain this one-to-one matching makes this package we call it inherently serial, meaning that each step kind of depends on the last step. And it's not able to be scaled to large linkage tasks. So as a last description of the types of models for record linkage, I want to highlight what I work on essentially, and I call it fast beta linkage. And it's kind of a combination of the two, where I relax that constraint and I use NB, many independent decisions, which is a relaxation posed by one of my collaborators, and then I modify it a bit. And we find that this has a minimal loss of accuracy from the BRL method, but large computational gains similar to the FastLink method. So it technically allows for these many-to-one matchings that are bad. Like this would be kind of bad. If we say two records in one set match to the other one. But we have these probabilities that we calculate through the model, and we could very easily decide to just choose the one that had the highest probability. So again, these the probabilistic record linkage techniques gives us these probabilities, which allows us to make decisions we might not be able to make if we are using completely deterministic methods. So those are the three different models. I guess I'll plow through and do a little bit more mathematics. Both models utilize what we call M and U parameters to model the data, one for matching, one for unmatched records. So we're going to define M with a subscript F and L. That's for field F and level of agreement L. That's the probability of seeing that gamma ij is the comparison vector for the ij record pair. F is the field equals L. So the probability of seeing that level of agreement given that the records match. And the UFL is probability of seeing that level of agreement given that the records do not match. So we could think of this M as reliability parameters that show how likely it is for a feature to remain unchanged across files. The probability that Karen in one data set is spelled again exactly Karen in another data set. And the U are these discernment parameters that show how unique the values of a feature can be. And the reason why that's important, because I'm going to show you this in the R scripts later on, is that we're going to multiply these parameters together for the relevant F and L to get Mij, the probability that the record is a match, and Uij, the probability that the records are not a match. And we're going to create this likelihood ratio, which is this Wij, a weight probability of the probability that they do match over the probability that they don't match. And that ratio is going to power a lot of the record linkage algorithms. And notice in just some basic mathematical intuition, this ratio is large when Mij is large. These are all bounded between 0 and 1 because they're probabilities. But if Mij is close to 1, then below, we want that number to be very, very small. We want big numbers on the top and small numbers on the bottom. And that's going to give us really high evidence that we should call a record pair a match. So that is most of the rigorous mathematics. Any questions at this point? I know we'll get maybe more tangible after this. I'll pause for a couple seconds. Okay, so some practical considerations. When we're constructing these comparison vectors, again, this is something that the packages all take care of. So we measure the distance between two fields using whatever metric we like, and then we threshold this distance into discrete values. So for example, this Levenshtein distance, I'm going to compare the name Brian with an I to Brian with a Y. I believe that distance would be one change divided by 5 total possible letters. I'll have a distance of 0.8. And we choose thresholds to use that to later classify the pair as a 1, 2, or 3, or whatever numbers we have chosen to use for that comparison vector. So we can use the easiest thing is binary agreement, male, female, just different or not. Even you can do it with names as well. Just if your name is exact match, I'll give you full agreement. If it's not a match, full disagreement. Or you can use multiple agreement levels to capture a partial agreement. I generally find you only really need non-match, partial, full match. Some people try to use non-match, possible, probable, very likely. Some people try to add extra ones. I find that it's not really necessary. An existing package, they perform this binary agreement, numerical distance, and string distance. So, like I said, many packages compare strings to the Norman-String Levenshtein distance. Additional metrics could be language specific, like soundex codes. And if you're not using a package, and if there's a longer, if you had time to be very, very careful about this, you'd want to think very carefully about these agreement levels. So for example, something to kind of ask for you guys, should a soundex match be regarded as a full match or partial match? What is one of the ones that we often bring up with maybe a Sandra, right? A Sandra, S-A-N-D-R-A, and maybe it's spelled with a Z somewhere else. Do you want to characterize that as a full match or do it as a partial match? I generally go for maintaining the purity of what a full match is, and that for me should be an exact match, but there's just some disagreement among other people, and you'll see that the default values in many of these packages allow some wiggle room in deciding what is a full match. So again, none of the packages are able to do, none of them at the moment are built for these language specific issues. And they can be edited. That would take a little bit of work, but someone can dig into the code and plug in a different function at a certain spot. But I found that using the normalized Levenshtein distance ends up working pretty all right, because even if Brian with an I and Brian with a Y get characterized as different, if these record pairs are indeed matching, you will get that match on Kuninger and Kuninger. You will get that match on my address and my date of birth and these other things. So despite the error in one field, and despite the error that we might have, that might be due to our own classification system, there's enough other information in the data to allow the algorithm to make the correct match. So that's one consideration for using these string distances. Another thing to keep in mind is that the record linkage model assumes that agreement levels are conditionally independent given the matching status of the records. And that's the case for most things you could think of. For example, one that is independent is birth month and birth year. If I tell you that two people have the same birth month, you know nothing at all about whether they have the same birth year. It doesn't tell you anything. Me and my brother were both born in July, and that does not tell you at all that we're what year we were born in. However, some fields are dependent. If records disagree on department, I'm talking to Columbia, so I looked up how the geography is broken up. If two records disagree on department or state, we know they probably disagree on the city also. So these fields are not independent. And if you use those two dependent features in the record linkage algorithm, you're essentially doubling down on information, and it just distorts things in a not great way. Again, I actually think that in the Columbia case, with the data from what has been described to me, with this like nearly unique identifier, that should be powerful enough to overcome a lot of these issues, but just something to keep in mind. So one way to get around this might be to create more nuanced comparison vectors, incorporating multiple features. So for example, if your data set has one feature called department, another one called city, we might define a agreement level just broadly called location. And we're going to give that a full agreement if it matches on both those features, city and department. A partial agreement if it's only within the department, and no agreement if it matches on neither. So that's creating one comparison score, incorporating information from two features in the data. And that's a way that I've seen in my work that improves results. Current packages do not execute this type of comparison. They're simpler than that, but it can be done. And depending on the types of fields, and again, depending on the data you have, you might just be able to plow on through, or it might be simpler just to omit one of those fields. So that's just one additional thing I want to highlight. And actually, what I really should have mentioned is gender. Actually, gender ends up being a dependent field with first name, because if you disagree on gender, you probably more than likely disagree on first name, in at least in English context and Spanish context. So I typically do record linkage not including a gender field, because it kind of doubles down on some of the information from the first name field. One other, oh, I should have done, oh, sorry about this. There's a slide that should be in here about blocking, which I'll talk about in the presentation, as in the later presentation too. But this NA times NB comparisons is just too much. If you're going to compare, the data that I saw maybe has one data set has 1 million records, one has 60,000. That is a number that I don't know. That must have like 15 zeros behind it, the number of comparison vectors you'd have to make. Mostly infeasible most of the time. So one easy way to get around this is to use blocking, which essentially is just running record linkage independently on different chunks of the data. You choose a feature that you believe to be high quality, for example, like a department, and you only compare records within that department. And then you're going to just run record linkage independently on each block. And the FastLink package has capabilities for that, which I will show you in just a little bit. There's one other approach to scalability, and this, apologies that I didn't have that blocking slide. When I send this out to you, I will add that slide back in. But another approach is this random sampling method, which you'll see in the tutorial that I send out. And that's where you run record linkage on a small set of the data. You learn these parameters, and then you just click and apply these parameters outside to other comparative vectors that you haven't seen yet, that you haven't seen before. And that's very tempting, but I believe in what you guys will be doing, blocking will be sufficient, and it's theoretically more sound. So I would advise blocking and to ignore the stuff about random sampling in the tutorial. This is kind of what I said. You may actually be able to do this whole thing at one time. It might take a couple like hours, but somebody can check that. It'd be kind of interesting to see. If not, you definitely should be able to do this by blocking on department, for example. You should not need this generation technique, and FastLink does not do these SoundX comparisons, but allowing for partial agreement on the strings should be sufficient, and you'll be able to get by with that. Those were the two biggest chunks of the presentation. These last two will be very fast, but I will pause for questions again for any questions about these kind of practical matters. Okay. So evaluation. There's just a few, when we have known labels, which is not often the case, but which you might yourself be able to produce on a small data set, like you hand verifying that certain record pairs are a match, or you might have a subset where the information is more reliable, for example. You can calculate these performance metrics. So one is called recall, which is the true matches that your algorithm found divided by the number of total true matches. So that is how many of the matches are you finding. Precision is a total matches declared. The true matches declared, sorry, I will fix that typo. The true matches declared divided by the total matches declared. So yeah, of the ones that you are declaring, how many of them are correct? And to balance these two metrics, sometimes you have these two metrics, it's hard to really compare two methods. So it's nice to have, because one's going to be good for one and one of the one's going to be worse for the other. So it's often better to combine these metrics into something we call F measure. And this is just kind of, it's a weighted way to kind of combine these two scores, which makes it easy to compare results. Without these known labels, checking the performance of record linkage is a little more difficult. And these are some things that I do, and which I'll show you how to do in one of the R scripts. So one, you could examine the histogram of match probabilities. And if the record linkage algorithm worked well, the probabilities should be very separated, with most records being a clear non-match and a clear match. So probabilities near 0 and near 1, and relatively few around the middle of like 0.5, 0.6, 0.7. You're going to want a clear separation of these probabilities. You're going to be able to inspect the Foleggi-Sunter weights that I mentioned. That's dividing those M probabilities by the U probabilities. And you can just do some sanity checks. The really impactful matching variables, like a name, will have a very high Foleggi-Sunter weight, and something less influential, like gender or like a city, should have a lower one. Also, a full match should have a higher value than a partial match, which again, I will show you. And then, you could just take it kind of informally and visually inspect. Just look at what the matches it pumps out and say, oh, would I think that that's a match? And that's a good indication. So all these are going to be shown in the Markdown file. And here are just, when I sent out this slides, where it says GitHub right here, it is a link. And it has the links to where you can get these packages. And my method is called Fable Fast Beta Linkage. That's not publicly available yet, but hopefully soon. And due to Danley's record linkage task, the scale of it, I'm going to recommend use FastLink. And that's what I'm going to show you right now. So, and then I have, these are the citations for those methods that I introduced to you today. So I'm going to stop presenting for the moment and see if there are any questions. Great. Okay, I'm going to pull up the first tutorial, and these will be kind of fast to go through because you'll have time over the next 2 days to play with these yourself. So I'm going to just full screen share. I think that works. Oh, yeah, I don't want that. I want. So if you go to that link that I have in the slide, you'll see this tutorial for FastLink. And it begins with the papers that that explain how it works and instructions about how to download it. Here's just the simplest way to download it through R. I would recommend using this other set right here, which gives you the newest version. This actually was updated fairly recently. This thing was like 9 days ago, which I only knew about because I had, again, dinner with the author a few days ago. So there was some new functionality I didn't know about. And so you're going to download it through this stuff right here. And this tutorial basically just walks you through how to run FastLink. Something to just keep your eye out for. You have time to look through this yourself, but in particular, it shows you, these are all these parameters, which I explained some of them in my in my slides. Yikes. Pre-processing matches via blocking. So this is going to be an important step for you guys to use, where you're going to block the data. You're going to have to choose your two data sets, and you're going to block on something like maybe department. And that's going to create an object that has the indices for the record pair, for the comparisons that you want to make. And then you're going to do a step like this that creates these smaller blocks, and then you're going to run record linkage on these smaller blocks. And then there is functionality for, there's different types of blocking as it explains. And then there is stuff here about, right here, about aggregating the results from those different blocks. And that should help you do record linkage at the scale that you want to do. You might be tempted to do this random sampling for FastLink on the whole data set, just so you have everything in there, and then you're going to take maybe 10% of the records. For reasons that are too mathematical to explain, I would suggest against that for the moment, and the task is doable through blocking. And I think that is everything in this tutorial that I want to show you. And then I just want to show something that I typed up. So here, I'm going to show you some additional checks that I do when I do record linkage. Oh, I should stop for a moment for questions on FastLink. Stop for a few seconds. Okay. So again, I'll be sending this to you, but I'm just going to show you some additional things that I do. So this is using something called R. There's a package called record linkage in R, and there's some data that is often used called RLData 10,000. This first page is just, that's one list of records, and methods are kind of different for deduplication within one list and record linkage across two lists. So this is all some messy code that creates two data sets from that one data set. Instead of one list, I've separated into two for me to do matching, for me to demonstrate the stuff to you. So when I run record linkage, I give some advice about constructing these comparison vectors. So by default, FastLink conducts these binary comparisons where features are assigned to 2, where matching features are assigned to 2, and non-matching features are assigned to 0. And we can use a partial match so that we can plug in a 1 in there for something we decide to be a partial match. By default, the thresholds are 0.94 to 1. Those are going to be an exact match, and 0.94 to 0.88 are the partial matches. I don't really like doing that, so I'm going to recommend assigning it to only to the full matches with string distance of 1, which is indicated here, and a partial match to string similarities between 1 and 9.9, which is indicated here. You can use the default setting. I'm going to recommend that you maintain the integrity of what a full match is and have it as a string distance of 1. So you run this record linkage. Now some things to examine. So you're going to get, I just did some code, manipulating some stuff. You can see these posterior probabilities. Most of the records, we have a very, very, very high certainty that things are a match. So you're also going to be able to set a threshold for what you decide to consider a match. By default, FastLink has it at 0.85. You can probably end up putting that higher to guard against potential false matches. Something I want to show is that here is the posterior probability for all of my declared matches. There's a chunk right here. Most of them are up here, like I said. Because I know this data, I know what the true matches are. And this is the matches, this is the posterior probabilities for those true matches. And notice down at this end, hopefully my mouse is showing, but down at that 0.88 level, we declared a lot at that level, but very few of them are true. I can also look at the posterior probabilities of the false matches, and I could see that disproportionately those ones were false. So that indicates to me that for this data set, a better threshold might have been 0.9, for example, instead of 0.88. Again, you're not going to know that ahead of time, but by visually inspecting and by looking at this histogram and kind of seeing where that distribution of the probabilities, you can make an informed decision about what to set that threshold. We can also just visually inspect some of these matches and non-matches. So here we can see that the types of stuff that Fastling's able to catch. So this first one, Henrik Stein, matches on everything except for the birthday, right? So no problem, we're able to find that. It was also able to capture that Schaefer right here is reasonably close enough to Schaefer here, and we're getting that as a match. Hans Schmidt. This is something that you should do. This is a Klaus that's misspelled Klaus and a other Klaus. These are all German names. This is something that you should do to kind of sanity check and make sure that the record linkage is working correctly. The last thing I mentioned were these Pileggi center weights. So we have these M probabilities and these U probabilities in these FS weights, Pileggi center weights, we calculate like this. And again, the fact that a 2 here gives this weight of 158 means that matching on a first name is a more powerful linking feature than some of these other ones. We also see that having a partial match on the first name still is a positive result. We still multiply whatever number by 20, for example, but that's nowhere near as strong as a full match. And again, a full disagreement on the first name diminishes that Pileggi center weight because this is a product, right? So numbers smaller than 1 diminish. And yeah, we see that birthday, birth month, and birth year are just not as strong as matching on first and last name. So you should check these, and if these things are out of whack, if birth year for some reason is astronomically high, or more likely actually something like the last name, this number is very low, then something's going wrong in the coding and the algorithm. And yeah, so these are ways to make sure that the variables that you think will be impactful are impactful. So in particular, the ID number that you guys use should have a very, very, very high Pileggi center weight. Last, this was just me calculating some of these evaluation metrics. This is actually very imprecise, but that's because this data set is made to mess you up and stuff that no record linkage would be able to find. So I typed up a couple of these guidelines for Danny. Let's some concluding thoughts. Your team should experiment with some of these different thresholds for the probability, depending on how much you want to balance false positives and false negatives. Since you have a nearly unique identifier, your data is probably reasonably clean, meaning it's not riddled with errors, you should expect to see a very stark separation with the non-matches and the matches. So you should be able to use a high threshold and maintain high accuracy. So maybe a 0.9 or a 0.95, you can play around with that. You're going to want to use string distance with partial matching for the name field, the address field, probably, if that's in there, binary comparisons for other features. Follow the guidance from the tutorial on how to block, and I'm going to recommend blocking on department, I think, if that's how your data is structured. If those blocks are still too long, you could do another blocking variable, either city within that department or just then within the department block male and female. Again, I'm going to recommend against that random sampling stuff. And when you check those Pelegi center weights, I expect that the identification number will have the highest weight. That agreement on the ID number will have the highest weight. And then the names will be the next and most impactful, and then the other features. So those are the 3 things I wanted to share with you, the kind of broad conceptual, how do I stop sharing? The broad conceptual overview of record linkage and the different approaches, and knowing that technically this other thing, beta record linkage, it's generally outperforms, but it's too limited to work at the scale that you probably want it to work at. Yeah, the theoretical overview, the basics of FastLink and how to run it, and some of my additional diagnostics. And that is all I have for you today. Are there any questions?
Yes, I had 2 questions. One is about if if there is a possibility that I have one record that matches 2 records, like with this probabilistic match, or it's very unlikely. And the other question I had is if I have large data sets, like for example, I have 7,000 million people in the HEIH survey, and I have about 10, 12 million unique IDs by for example, the statistics about employment. Which method do you recommend about? And I have the question, I understand that you recommend random sampling, but I was not aware of, since I see that it's random, so I can link all the data sets, all the records that can be matched with this method. And more, thank you.
Yeah, so the second question about which method would be good for matching 7,000 to about 10 million, I'm going to say still the FastLink method. Within that you might be able to just plug those 2 data sets into FastLink as it is. But again, if not, you can use the methods that are in that tutorial to do the blocking, which would take some key and then make a couple smaller linkage tasks. I was playing around with FastLink the other day, and I was able to do a comparison of like 1 million to 100,000. It made my computer very slow, but it was able to do it. So yeah, FastLink, and if you need it, you do the blocking. I did not catch your first question, however. Sorry, somehow the sound went weird.
I was wondering if with this fuzzy match, I may have like 2 names that only change 1 letter, one from the other, but at different people. But if it may record them in the match, it may have it like it records, or the distance is not long, but they are different people. So I was wondering if one record can matches 2 other in the other.
Yeah. So that's a good question. So they're different people, and the fuzzy match, it says their names are kind of close. It might be the case that your string distance function ends up saying that it's matching on that first name. However, by using the other information in the data set, like the unique ID, like the department, like the birthdays and all that stuff, it should be able to identify that those people are not the same. So again, just because the comparison vector identified one field as matching, the benefit of probabilistic record linkage is that you're going to use information from all the other fields to end up deciding what's a match or not. So in your case, if they're different people and the other information is reasonably different, then you should be fine.
Okay, thank you. Bye.
Any other questions? So something that we had scheduled, or there should still be scheduled another meeting for tomorrow or Friday, which I will communicate with Karen about. And that would give you all a chance to play with some of this on your own and come back for to ask more questions. I'll also be available by email after like this official Data for Now project is ending soon, but I will be available for some questions by email afterwards, and my email will be in the slides and you guys will all have it. So there's that. Yeah.
Well, thank you so much, Brian, for this very detailed technical training. In addition to the theory, you also showed basic code as well, how it is run, and then you also gave a few examples. And then hopefully we will share all this presentation along with all the codes to colleagues here, and then maybe they will try to run it as well. And then I believe either tomorrow or day after tomorrow, maybe Gabriel and Brian can agree on the date and time and have a meeting together to do a final hands-on work on the actual data if it is needed, and complete this record linkage part of whatever is left. No, although our project is almost coming to an end, as Brian also just said, like our collaboration is still there. We have worked so long, so much, and we will be continuing to support as it is needed in the future. So with this, maybe I will give maybe Gabriel or anyone from Dane to say anything before we close the training.
I was talking to Karen, and I believe that Friday will be okay to update, like to see the presentation and to manage with the data we have.
Do you have any, well, you guys can email me the time you're thinking for that too. Yeah.
Sure, I believe in the afternoon will be good. About this hour, is this okay to you?
If it's possible a little earlier, but we can, if 3 is the only time, like that's fine also. Like, yeah.
All right, let's schedule this through the email when it happens. So I'll just give the floor to Howie at the moment.
Just want to say whether today's Wednesday, right? Friday, if the colleagues can take the code that the Brian's going to share and the presentation and give it a try to some of the work you have in your hand with the data, and then you can come back with questions on Friday for Brian.
And right here, there's more people than are on my normal email thread. So I will email you, Samrat, the stuff, and then you can email it out to everybody.
Definitely, that
Okay.
works. And so thank you so much for participating. If there is any, I'll just wait for any hands or any final comments before we close the training session today. Looks like we do not have any comments. So one more time, thank you so much, Brian, for conducting the training, and the whole team from Dane and UNST as well for participating. So we will share this recording as well in our Data for Now website. So thank you so much for attending and presenting. Thank you.
Thank you, Brian. Thank you, everybody.
Bye.
Thank you, Brian. This new page on the chain. So Friday 11 is okay. Sorry to talk.
Friday, yeah. Gabriel, can you send the email to Brian and us as well for the meeting? And then also the recording of this, please, training.
Sure, I'll send it to you.
Thank you so much. All right, have a wonderful day. Bye-bye.
Bye.
Bye, thank you.